Hi everybody, Dr. White here, working still on figuring out whether infinite series converge or diverge. In this section, I want to look at infinite series that just have positive terms. So the terms an, they've got to be bigger than 0 for all of the n that you're working with. Now, when we've looked at infinite series, I think you've probably noticed there's a similarity between infinite series and improper integrals. You know, when you're looking at an infinite series, you are looking at a limit of partial sums. You're saying, hey, I'm going to add up the terms of the series from a1 up to an. I'm going to stop there. But then I'm going to imagine that capital N gets bigger and bigger so that I'm adding up more and more terms, and I'm going to look at that limit. And that should remind you a whole lot of an improper integral where you say, hey, I'm going to find the area under the curve from 1 out to some number n, but then I'm going to let n get bigger and bigger, and that way eventually capture all of the area under the curve all the way out to infinity. And there's that same issue, there might be finite amount of area under that curve, there might not, When all your terms are positive, every time you move out further in your series, take a bigger partial sum, you're adding on, you're getting a bigger sum. And when this function is positive here, as you move the n out, you get more area. And so really the question is whether you level off at some finite area or you go just up to infinite area. Similar here, are you going to level off at some finite number for your infinite sum, or will the series sum to infinity? But this relationship here is so close that there's actually a theorem that we can make use of. It's called the integral test. So let's say that when you look at the general term for an infinite series, an, that you can think of it as f of n, where f of x is a function on real numbers, on the real numbers from 1 to infinity. And suppose that function is positive and continuous and decreasing on that interval of real numbers. Then there's two facts that can be useful. If the improper integral, the area under f of x from 1 to infinity, converges, if that area is finite, then the sum of the infinite series is going to be finite. On the other hand, if the area under that curve f of x is infinite, then the sum will be infinite. Okay? I want to show you why that is true. So look at this picture here. Here's a graph of y equals f of x from 1 on out, and you can see that this is it's got positive values, never goes below the x-axis. It's continuous. I can draw it without lifting my pencil, and it's decreasing. Okay. Now I'm going to make rectangles underneath it. So like at 1 on the x-axis, f of 1 would be up here, and that would be the height, that would be a1, okay? There's a rectangle here whose width is 1 and whose height is a1. But that rectangle does not lie underneath the curve. It's just out there to the side. Now look at this next rectangle. This rectangle's height is determined by f of 2 up here. That's a2. And so the rectangle has height a2 and base 1. Its area is a2. And similarly, there's a rectangle whose area is a3 between 2 and 3, a rectangle whose area is a4 between 3 and 4, and so on. All these rectangles, they lie underneath the f curve, okay? So if I just kept going like that, making an a5, a6, and so on forever, I would have the sum a2, a3, a4, and so on. That sum would be the sum of the areas of all those rectangles. And you can tell that the area under the f curve from x to infinity is going to be bigger than that sum. So if the area under that F curve were finite, if the improper integral were to converge, then that would mean that that sum from 2 to infinity of an would have to converge. Now, if you add on an a1 to that sum, you're only adding on a finite amount. So that's telling you that the sum n goes from 1 to infinity of an would also converge. Now let's look at the same situation with the same function f of x, but this time I'm going to make a little bit different rectangles. For the rectangle between 1 and 2, I'm going to let its height be determined by the left-hand endpoint. And so this height here is f of 1, which is a1. And here, the height determined by the left-hand endpoint is f of 2, which is a2. And so the areas this time are going to be a1, a2, a3, and so on. So you'll notice this time, the rectangles lie over the curve. So the area under the curve from x is 1 to x is infinity would be less than the sum of the areas of the rectangles, which is the a1 plus the a2 plus the a3 forever. So if we were to find that the area under the curve were infinite, if the improper integral were to diverge, then we would know that the infinite series diverges as well. So finite area under the F curve tells you that the infinite series is finite. Infinite area under the F curve tells you the infinite series diverges to infinity. So let's try out an example. The harmonic series is the series 1 plus a half plus a third plus a fourth and so on forever. So you write it like this if you want. And I'm wondering, does the harmonic series converge or diverge? You know, it's not a geometric series, so I can't just pull out that theorem. The terms of the series converge to 0, so I cannot say that the series, I don't know if the series converges or diverges. If they had not converged to 0, then I could say by the kth term divergence test that this infinite series diverges, but the terms converge to 0. Certainly not some kind of general term that we could break up into two fractions like in a telescoping series. So what are we going to do here? Well, consider f of x equals 1 over x, the function associated with the term 1 over n. That is positive and continuous and decreasing on 1 to infinity. So let's look at the improper integral from 1 to infinity of 1 over x. Well, hey, I can write that improper integral as 1 to infinity 1 over x to the first power. And remember, back in the section on improper integrals, there was this p integral test for them. Integral from 1 to infinity 1 over x to the p power here. If the p was less than or equal to 1, then this would diverge. If the p was bigger than 1, this improper integral would converge. Well, this time the p is 1, which is less than or equal to 1, so this thing is going to diverge. Or you could just figure it out again for yourself right here and now. In fact, they do that in the textbook. They have this example in the textbook. And you take the antiderivative and its log of x, and you evaluate, and you take limits, and you get infinity. So the improper integral diverges, therefore the infinite sum has to diverge by the integral test. The 1 over n's go to 0, but they don't go to 0 fast enough to prevent the sum of them from being infinite. Actually, this p integral theorem for improper integrals, it leads to a theorem for infinite series. Theorem 3 in the book, called Convergence of p series. The infinite series sum n goes from 1 to infinity of 1 over n to the p. It'll converge if p is bigger than 1, and it'll diverge if p is less than or equal to 1. And all you got to do is just use the integral test on it. Look at the integral from 1 to infinity of 1 over x to the p. and check to see whether that converges or diverges. So very quickly, we suddenly know a lot about a lot of infinite series. Like we can tell this infinite series here converges because it's a p-series where the p is a 2. That's bigger than 1. So I can say this converges, and my reasoning here is just it's a p-series, the p is bigger than 1. I want to point out, though, just because we know it converges doesn't mean that we know what it converges to. The associated improper integral, we can find what that converges to. In fact, we've done it before. And it turns out it converged to 1. The area underneath 1 over x squared from 1 to infinity was a 1. But that's not what this series converges to. You can actually prove that this series here converges to pi squared over 6. That was a very, very difficult result that was proved in 1728 by the mathematician Leonhard Euler. So I stress that the integral test only helps you decide convergence or divergence for your infinite series. It doesn't tell you what the infinite series converges to. The definite integral, the improper integral, when it converges, what it converges to doesn't have anything to do, really, with what the infinite series is going to converge to. Let's check out this infinite series. I can factor out the 5, and I can write the cube root of n as n to the 1/3, and all of a sudden I'm looking at a p-series where the p is 1/3 less than or equal to 1, and so I know this thing diverges. Here's another strategy for figuring out if an infinite series converges or diverges. It's called the direct comparison test, theorem 4 in the book. Suppose you got 2 sequences. One of them is an, the other is bn. And suppose the ans are positive, but they're always less than or equal to the bn's. Well, they don't have to be always less than. For sufficiently big n's, they need to be that way. Suppose that for some capital M, this happens for all n's bigger than or equal to that capital M. So it's not like A1 has to be less than or equal to B1, and A2 has to be less than or equal to B2, and so on. It could be that this relationship doesn't start happening until maybe the n's are bigger than or equal to 5, or 15, or 52, or something. But as long as this starts happening and keeps happening for the rest of the n's, then we're in a situation I want to look at. If the sum of the bn's converges, then the sum of the an's converges. This should make sense. If these numbers add up to a finite number, since the b's are bigger, then the a's ought to also add up to something finite. On the other hand, suppose the sum of the an's is infinite. Well, since the bn's are bigger, they ought to add up to something infinite as well. And so if the sum of the an's diverges, the sums of the bn's also diverges. So let's see how this might be useful for us. Suppose we're looking at this infinite series and we're wondering, does it converge or diverge? Okay. Well, I notice that this is similar to a simpler general term, 1 over 3 to the n. And so let's see, can we show, is it less than it or bigger than it? Well, let me see. This time it's less than it, because 1 plus 3 to the n would be bigger than 3 to the n. So when you divide by something bigger, you get a smaller number. So this is true for all n's that are at least 1, that's for sure. Now, I also know that the sum of these terms, this thing here, I know that has to converge, because I could, if I wanted, write it as a geometric series where the ratio would be 1/3. You know, I could write this here as a 1/3 to the n, you know? And so it doesn't matter like what this converges to, it's just that it converges. Therefore, this smaller series converges. So I'm using this part 1 of the direct comparison test here. I found a simpler series, sum of the 1/3 to the n, that converges. My series was smaller than it, so it also converges. Here's another example. Does this converge or diverge? Well, again, I try to think of something simpler I might compare it to. So I look at n plus 1 over n to the 3/2, and I notice, you know what, that's going to be bigger than n over n to the 3/2. And that actually just reduces to 1 over n to the 1/2, which is certainly a simpler series. So my terms are bigger than these terms. Let's look at what happens to the sum of those terms. Well, that diverges because that's a p series where the p is a half, which is less than or equal to 1. So this diverges. Therefore, my infinite series diverges. I am using, this time, the second part of the direct comparison test. This time, my bn's were the terms of my actual series I was curious about. And the an's were the 1 over n to the 1/2 that was smaller. The sum of the an's was infinite. Therefore, the sum of my bigger terms was also infinite. Now, sometimes you'll find like an an less than a bn, but the sum of the an's converges. That will tell you nothing about the sum of the bn's. Because if you're bigger than something finite, you could be finite or be infinite. Similarly, you might find an is less than or equal to bn, and you might find that the sum of the bn's diverges. Then you can't tell about the sums of the an's. If you're less than something infinite, you might, be infinite, but you can still be finite. So you only get to use this direct comparison test in these two situations here. When the series you're interested in is less than a convergent, or the series you're interested in is bigger than a divergent. So it's a little bit tough test to use sometimes, but it's really there. It's worth it. But let me show you a time when maybe it's just too tough to use. Does this infinite series converge or diverge? Well, I could try comparison. I could look at my complicated terms, and I could say, you know what? This is actually less than 1 over n. Like log of n squared, that gets big when n is big. So if I stop dividing by it, I'm dividing by less. So this would be more. The problem is that this diverges. P series, p less than or equal to 1. It's a harmonic series, actually. So me being less than a divergent, I don't know about me yet. Maybe I could add to infinity too. So let's try something else. Hey, maybe, when I look at this, that looks like if it were a function of x that I could maybe find an antiderivative. Let's see if we could do an improper integral here. So looking at sum n goes from 2 to infinity here, let's look at the improper integral of 1 over x log of x squared from 2 to infinity. This would be good to look at because that function there is positive, it is continuous, and it does decrease from 2 to infinity. So let's try the improper integral. I think first I'll just go for the antiderivative here. And I'll make a u substitution. U is log x. Du would be 1 over x dx. I see a 1 over x dx right in here, so I replace it with a du. I'm left with a 1 over u squared. So I got to find the antiderivative of u to the negative 2, which is minus u to the minus 1, minus 1 over u. So the full family of antiderivatives is minus 1 over log of x plus arbitrary constant. So if I want the improper integral, I could just do fundamental theorem of calculus. I could just do the integral from 2 to the n, 1 over x, log of x squared dx, take the limit of that as n goes to infinity, and get this with the fundamental theorem of calculus. So antiderivative evaluated between 2 and n. Here it is here. Take the limit as n goes to infinity. Well, minus 1 over log n goes to 0, so we're only left with a minus 1 over log 2. And that's finite. So this improper integral converges, therefore this infinite series converges by the integral test. So, if you can't find another series to compare to that compares in a helpful way, that you can use the direct comparison test, don't worry, you could also try the integral test on your series. Okay, that's enough for now. Next time we get together, we'll look at one more, the limit comparison test. Get another little tool in our toolbox for figuring out if infinite series converge or diverge. See you soon.